for single chain protein using another metric, which is GTTTS, captures sort of the global properties and the global features of your protein. And again, on GTTTS, we are achieving the same performance, almost the same performance as AlphaFold. AlphaFold predictions on CASP are 74.6, and our predictions are 73.8. So in a nutshell, we have re-engineered from scratch AlphaFold 2, but we have also achieved parity for monomeric prediction. Oops. Yeah, the screen is not, it's frozen. That's one. Okay. Okay. So now that we have this platform that is highly accurate, achieving sort of state-of-the-art accuracy for, again, monomeric proteins, and this platform is trainable, what have we learned from retraining AlphaFold 2 and how this is important, I believe, for the community beyond protein structure prediction? So our manuscript is out there, so you can read more about the kind of insights we have learned. I have picked few insights that I believe have sort of conclusions that are beyond protein structure prediction. So the very first observation we made by retraining AlphaFold 2 and OpenFold is that we observe a very fast convergence. So this is a sort of training curve, again, tracking the LVDT metric, the higher the better, one being a sort of perfect prediction. At the end of training, we achieve a performance of 0.9 LVDT, but the fast convergence is that we achieve 90% of final accuracy in only 3% of total training time. And I believe this is a very important performance because training and retraining and exploring new modalities using systems like AlphaFold is very expensive. Typically, you need a large cluster. But because the convergence is very fast, one can test ideas in an extremely kind of efficient way. So for instance, if you have a cluster with a dozen of GPUs A100, you can reach this level of accuracy in less than a week. So this really suggests that now one can start exploring variants of OpenFold with far less compute than what you might have expected before seeing this kind of training pattern. On the other hand, we do have certain advantages on top of being and achieving parity with AlphaFold 2. Our pipeline is faster at inference than the original AlphaFold 2. We are up to 3 times faster on proteins that contains less than 1,000 residues. And on the other hand, we are also more efficient. We can provide inference for longer chains than the original AlphaFold 2. We can go up to 4,000 residues on a single GPU, which was not the case for the original AlphaFold. So these are kind of more features about OpenFold. But now let me turn to the most important observation we did while retraining OpenFold. And I hope what I will convey that this observation might provide strong reasons for optimism to extend machine learning and deep learning beyond protein structure prediction. So let me briefly turn to LLMs, large language models, because they are setting the stage. Much of the kind of architectural innovation in the field, including transformers, are coming from large language models. So some of you might have seen recently this sort of evolutionary tree capturing the evolution of LLMs from GPT-1 to the latest GPT and BERT and many other kind of implementation. And one reason really to understand this evolutionary tree, the progress, is understanding how those systems scale. So scaling and understanding how LLMs scale is an integral part for understanding this evolutionary. So what do I mean by scaling? So a question that is asked in the field is that how we understand the performance of those large language models in terms of the number of parameters used during training, data size, and compute. And maybe sort of as expected, what we have learned is that the performance, which is here plotted with the y-axis, the lower the better, scales following a power law in terms of compute, data size, and parameters. So this really kind of helped us to kind of move to the next step and extend the architectural kind of performance. I believe that understanding scaling from machine learning application to biology is even more important for a reason that, unlike LLMs, data is not easily available for scientific purposes, and including for proteins. As you know, on the structural side, we don't have a large amount of data available in PDB, and generating those data is very expensive. So therefore, the question is, how can we understand the scaling of AlphaFold 2-like system in terms of data size, and then what kind of conclusion we can draw by doing those analyses? We would have loved to do a systematic analysis in terms of compute data size and parameters for AlphaFold 2-like system, but this is very expensive, and we didn't have like compute resources for doing a thorough analysis. So I will focus on data size. Okay, so let me unpack now this plot. So we start first by training AlphaFold 2 and OpenFold using the available data in the PDB. So in the PDB, we have roughly 130,000 non-redundant chains, non-redundant proteins. So that's the starting point, which is here the red curve. So when training OpenFold using the PDB data, we achieve a performance that is slightly above 0.8. So the next question that we started asking, what will happen if we randomly sample data from the PDB and we reduce the amount of data that we are using, so that we start answering the question about correlation between the system performance and the data. So next, we kind of sample 15,000 proteins from the PDB. This is the curve in yellow. And what is remarkable, and to our big surprise, is that even when training the system using only 15,000 proteins, substantial reduction with respect to the starting data set, we still achieve the same performance. Then we decided to keep reducing our data set. So we picked 10,000 randomly kind of proteins, and we still achieve the same level of performance. So unlike what we see pretty much across the board in machine learning, in proteins and in protein biology, the scaling between data size and performance is very different and very subtle. And I'm happy to tell you a bit sort of my kind of hypothesis why this is the case. But we kept reducing the data size. We went to 5,000 proteins. This is where we started observing sort of reduction in performance. But as you see, this is not a dramatic reduction in performance. And we have even trained the system with 1,000 proteins, blue curve, and there is, again, reduction in performance. But what is important to notice is that the LDDT is higher than 0.6. This suggests that a system based on an OpenFold architecture, using only 1,000 protein may outperform any existing pipeline prior to AlphaFold. We haven't done kind of systematic analysis, but this is suggestion. And again, all this analysis in a nutshell is suggesting that maybe the bottleneck for those systems is not the data. It's the kind of architecture and the type of inductive biases that we use for building an architecture. A nice thought experiment that we have in mind, and I hope we can kind of run this experiment, is the following question. Imagine that we only had 1,000 proteins in the PDB. Are there ways of jumping from 1,000 to 130,000 performance using a technique well known in machine learning called self-distillation that was also used by AlphaFold 2 and OpenFold? So I think it would be extremely interesting to kind of answer this question. Can we start with 1,000 proteins using self-distillation and reaching and again the final performance using a whole PDB? So this question is extremely important, and I think the conclusions that we are drawing are much larger and broader than like protein biology, because they raise this question: what are the conditions for having successful pipeline in biology broadly, in structural biology beyond protein structure? So this is just a plot to highlight the difference between proteins and RNA. So what you see here on the left, these are the total chains available in the PDB for proteins. We have over 600,000 chains. Now, if you turn to RNA, we have about 10,000 non-redundant chains in the PDB. So therefore, the question is, are there reasons to believe machine learning, deep learning could successfully take the data in the PDB, fold RNA with high accuracy. One possible answer is to say there is no reason for believing that deep learning might work, because we have very little data, but the analysis that I shared with you may suggest that deep learning might also work for situations where data are sparse, and the RNA is just an example among many others. I would mention maybe briefly now another aspect that we have analyzed, which is about diversity. So my previous analysis suggests that, again, machine learning, deep learning for biology and structural biology is not about data size. So we did ask the question whether it is about data diversity. We know that protein folds, they come under different categories. This is from the CAT classification. Proteins can belong to different classes, architectures, and topology. So therefore, we did ask now, what is the impact of training the system on subclass or subclusters from the architectural or topological perspective? And again, here, we see a drop in performance. This is an example where we look at specific classes, mostly alpha protein and mostly beta protein. And what we observe is that if we train only on alpha proteins or beta proteins, there is a drop in performance. But again, the drop is not dramatic. We are still achieving better performances than most systems that were released before alpha 14. So there is a correlation between data diversity, but it's not as critical as we might have expected before running the analysis. Maybe for the interest of time, I will skip that. We also looked at topology split and architectural split by clustering those kind of categories. So we start with using all the architectural and topological clusters, and then we start reducing. And by reducing those clusters, we see that there's a drop in performance. But overall, still, AlphaFold 2 is very robust. I would be happy to kind of share my hypothesis maybe during the discussion session. But I think all this analysis might suggest that AlphaFold 2 might have learned something implicit about the physics of those proteins. And therefore, the number of data, the type of clusters, type of topologies and architecture that we use do not matter much if the system was able at some point to capture some physical features about protein structures. So let me conclude briefly with some next steps, what we are doing. So I said earlier, the main scientific advantage of OpenFold is the ability of retraining the system and asking novel questions that were not covered by the original AlphaFold 2. So what are we currently doing? So first of all, we are retraining AlphaFold 2 multimer. So as I said earlier, immediately after the release of AlphaFold 2, DeepMind added this ability of folding complexes. We are almost there. So soon we will release weights for an OpenFold version that is now folding multimers instead of monomers. But now we are starting to ask novel scientific questions. So predicting how proteins bind with small molecules, drug-like molecules, a very important question. I don't need to explain to this audience why this is important for biology and also to some extent drug discovery. So now we are building a pipeline that is co-folding proteins with small molecules. So instead of taking as an input protein sequences, their MSAs and templates, and feeding this into OpenFold in a sort of two-stage manner in the Evoformer structure module, we're adding also a two-dimensional graph as an input and a track that is allowing the communication between features from the ligand molecules and proteins, and then having a system predicting proteins and how they bind with small molecules. And this approach really is based on the idea that co-folding is more efficient and more powerful than docking. So I will here very brief and comment about some of the recent works in machine learning and deep learning that are considering sort of docking small molecules with proteins. And again, for reasons that I have explained earlier, docking is typically artificial. So if you are doing machine learning for docking, start with your complex, take the protein apart, ligand apart, and you want to dock them again against each other. But as we know, proteins and ligands are not sort of rigid rock objects. Take them apart, they may exist in an artificial conformation, whereas our system, because we are co-folding the proteins with the ligand, we are not making assumptions at the beginning about the conformation protein. This will be picked by the system itself. And we do hope also that maybe our system will allow us to capture signals, distinguishing between apo and holo kind of structures, because in our pipeline, we are not only now taking proteins with ligand, proteins in the PGB exist in an apo state without any cofactors or ligand groups for the protein without any other kind of partner. Another very exciting thing that we're tackling is like going back to the original Enfys vision. So if you may remember, the idea of predicting protein from structure started to a large extent after the observation of Enfys and his group, suggesting that there is a map from sequences to structures. This is not how AlphaFold 2 and all the existing systems work. They don't take you from your sequence to your structure. They have all those intermediate steps. They compute MSAs and templates, and then they form proteins. And I mentioned earlier the system inability at capturing mutational effects, capturing with high accuracy proteins for which we don't have evolutionary information. And we believe that our pipeline that we are training now, that starts with sequences, could at some point provide highly accurate predictions without using evolutionary information and templates. And it might, more importantly, provide better insights about the physics of those proteins. We are also revisiting the question of predicting RNA structure from nucleic acid. As I said earlier, we don't have much data for folding RNA in the PDB, but taking at face value our analysis and data analysis for AlphaFold 2, the idea is that if we come up with the right inductive biases, we may see some progress for folding RNA from sequences. I don't know how are we doing with time. Okay, good. Yeah, so maybe, yeah, so the team, OpenFold is a team. So this is the core team, very talented students at Harvard program. I believe all of you know Mohammed. I would like also to thank OMSF for their help and other partners that helped us for kind of training our system. Because we have a few minutes, maybe I wanted to mention also one long-term vision. So I did say we are tackling multiple kind of aspects that are beyond protein structure prediction, RNA, small molecules, so on and so forth. And really, the long-term vision is to have a large multi-model for biology that could learn pretty much all the chemistry that is involved in biology, living organisms. So this is just a quote from GPT-4. I believe I don't need to tell you much about GPT-4, but one kind of reason to understand the success of those systems is that they take multiple modalities, images and text, and maybe other inputs, and they build those kind of large multi-model approaches. The really idea here in biology is that we don't have an experimental way to query the chemistry of living organisms at scale. We cannot like look at the cell and see all the type of interactions between proteins and RNA and small molecules. And I don't believe that in the near future we will have experimental techniques that will allow us to answer questions about the chemistry of living organisms at scale. And what AlphaFold 2 really is suggesting is that it might be the beginning of a journey. It's a bit like the AlexNet moment for machine learning. And we might be slowly able to build machine learning and deep learning pipelines that account for different modalities that are involved in the chemistry of life. And therefore, maybe the AlphaFold 2 true power is not about proteins. It's really about how we should think about cells and maybe at some point organisms by capturing in a multi-model foundational fashion all the chemistry that is involved in living organisms. I think it's the right time to start. Yeah. Thank you very much for it.
We have a question in the back over. I can understand how it works with the different process. If you want to use something, for example, to affect the potential. Yeah. How does that work? Will it stay the market